Hello, I'm Dr. Malescu, and I'm going to do a little quick review on chemistry for anatomy. So what is that? It's really biochemistry. It's understanding the chemistry of the body, okay? So we're going to keep it real simple and short. This is my own PowerPoint that I've created that's very easy to read, short and sweet. You're more than welcome to go over the PowerPoint that was given to you, but this is more of like a outline or study guide, and I'll post it along with my video to help you remember some terms, okay? So this is basically the Cliff Notes version of the chapter that I hope that you read, because it is important, and there's a chemistry assignment that you have to do. So you do need to read the chapter and read that PowerPoint that was given to you. But like I said, this is the Cliff Notes version, short and sweet, summarized, so that I can complete this video without boring you to death, because chemistry can get a little bit tedious. So I'm going to try to keep it exciting. I got my voice back. I wasn't sure if I was going to have it, so I was thinking maybe by tomorrow, but I did have laryngitis for a good 5 days. It started on Sunday. So of course I couldn't talk Monday, Tuesday. I did my micro video yesterday, so I'm slowly improving. This is not my normal voice, but at least you can hear me, hopefully, and we can get this completed. And hopefully this will help you with, what you have to finish out this week. All right, so first thing, the first term that you need to remember is matter. Matter is anything that has weight and takes up space. So if you want to write these on index cards and I don't want you to just memorize it. I want you to understand what is matter. So matter could be anything. Matter could be this pen, right? This book, me. So anything that has weight and takes up space. Elements are the basic building blocks of matter and cannot be broken down by chemical means, all right? So molecules can be broken down, which we're going to go over in a few minutes. So atoms are actually the smallest unit of an element, and that's the definition, and that it retains the element's physical and chemical properties. So an atom has the elements that that surround it and contain it, and so the atom, we're going to go over what does it consist of: protons, neutrons, electrons. So these all come together to form an atom, and bunches of atoms form together to form molecules. So it's a universe within a universe within a universe. So don't worry, you're not going to have to memorize the periodic table, but these are the elements found on Earth, okay? Are there possibilities of other elements that we do not know of in another planetary system, in another universe, in another galaxy? Yes, there is, okay. But this is what we have here on Earth. So hydrogen, helium, lithium, beryllium. So you can go down this line and you can see that we have a method to this madness, the way we chart it. This includes atomic number, atomic symbol, and atomic mass. So we're going to go over each of these and what it means. These are the symbols, okay? But you can write the whole thing out, okay? Hydrogen, right? Sodium, which is Na. K is potassium. Don't ask me how they came up with that. But at any rate, that is the periodic table. Unless you're taking chemistry, don't even worry. I'm not going to hold you accountable for that. Let's go into understanding the components of atoms. So the components of atoms are neutrons, protons, and electrons. Neutrons have a neutral charge. Protons are positively charged. Neutrons and protons make up the nucleus, the center, the core, okay? So positively charged protons, P for positive, protons are positive. Neutrons do not have a charge, they're neutral, and they reside in the nucleus at the center. Now, guess what? The neutrons and the protons make up the nucleus, but surrounding that nucleus are electrons, which are the opposites, kind of like when you think of batteries, right? And you put them in and you see the positive and the negative. Same thing, you have electrons are negatively charged, and basically they're going to be opposite charge of what the protons are. So if we look at this if we look at this atom, not molecule, we're not there yet, hydrogen, ion, we know that the nucleus consists of a neutron, which is, like I said, neutral charge, and a positively charged proton, one proton. Guess what? So one proton inside that nucleus, then we have one electron circling it to balance things out. So here it is. We have one proton, that's the atomic mass, has a charge of +1. Neutron has no charge, it's 0, but it has an atomic mass of 1. The electron that circles it has a negative charge, -1, and has this atomic mass, very tiny. And together, it makes up this hydrogen ion. Now take a look at carbon, nitrogen, oxygen. Now, why do we even have to go over this? Why? I mean, you're not going to be doing chemistry, right? You're going to be going into nursing, whatever it is within nursing. So you're probably not going to really have to know this. Wrong, because anytime we do any kind of testing, there we are, we can use the knowledge of chemistry and use isotopes for visualization of the organs. Voila. So what is happening here is an isotope are atoms that have the same atomic number, but a different atomic mass because the number of neutrons are different. Interesting. So all we're doing is changing the number of neutrons. Okay, so why does that have anything to do with say an MRI, CAT scan, or whatever else we can do in terms of radiography? Well, let's tell you, the radioactive isotopes are useful in dating old objects. We use that imaging body organs and tissues through X-rays. So this is why we don't want to use X-rays too much, because it can cause cancer. It's radioactive. Okay, but we can also use it to kill cancer cells. Amazing, right? Radiation, obviously, you know, can be harmful to the damage, it can damage the cells and be harmful to DNA. All right, now let's go over molecules. We just went over what an ion is with the positive and a negative. Positive being proton, negative being electron, and in the middle, the nucleus with the neutron and the proton. What are molecules? Well, they're just a bunch of atoms together that are bonded. Now, there's different kinds of bonds. There's really strong bonds and there's really weak bonds, like ionic bonds. So that's what we're going to go over. So molecules are made up of atoms that are bonded together, and it could be made of the same atom or different atoms. So if we look at ionic bonds, these are positive and negative. So if you put sodium chloride together, they make a really good team until you put it in water and they dissolve, which means that they were like a high school couple, okay? They were on and off again, right? So not a very strong bond. They break up right away, okay? So sodium and chloride, you add water in the mix and boof, they break up, okay? And that's why it dissolves. So that's an ionic bond. Very different than what we're going to go over in a minute, covalent and all that. So ionic bonds are weaker bonds. Atoms of this type basically are donating or taking on electrons. So what's happening is the outer shell contains an electron that it can share or donate. So in this example, we have chloride here, and it has this ion that is going to bind it with the sodium because it's going to come together. Sodium by itself is unstable, but with chloride, it's stable. And so they stick together. Problem is, you put water and it dissolves, as I said. This is the most basic explanation that I can give you without having to teach chemistry, because I'm not teaching you chemistry, I'm teaching you anatomy, but we have to go over this because it's part of the foundations of understanding the body. The body at its smallest level, at the molecular level, atomic level, it's all chemistry, all right? And so we start out small and we go in layers from the atomic level to the molecular level to the macromolecules, that help assist in metabolism of cells to organelles, from organelles to cells, from cells to tissues, from tissue to organs, from organs to organ systems, and organ systems coming together to make a human organism, and a human organism is part of a population, okay? So a universe within a universe within a universe. So we're looking at the smallest component. Okay, so let's go back and look at now the covalent bonds. Covalent bonds are basically atoms of this type sharing electrons, whereas ions, one was donating an electron because one was positive, one was negatively charged, and they got together. There was that attraction between positive and negative, and as soon as water hit, boom, they break up. Covalent bonds are different. They share, sharing is caring, and they share electrons. And so the outer shell is now stable, because you can have an inner shell and an outer shell of electrons that surround the nucleus, which of course contains protons and neutrons. Okay, so this is what we're seeing here, is that the outermost shell here has the electrons that will be shared with these two hydrogens. So here's this oxygen, and here's this oxygen that has 1, 2, 3, 4, 5, 6. Again, 1, 2, 3, 4, 5, 6 electrons in the outer shell. Out of the 6, 2 are going to be sharing with these two hydrogen ions. Okay, well, by themselves, they're not very stable, but they're very stable when you mix with oxygen and you make water. They share. So in other words, the 2 electrons from the oxygen are shared with the hydrogen. Okay. Now, if you look at this electron and this electron, each one surrounding this hydrogen, take a peek. You're sharing one from the oxygen, one from the actual hydrogen. Same thing here. One from the actual oxygen and one from the actual hydrogen. And that is the bond that water has. Water, in addition to the covalent bond, also has polarity, which we're going to go over in a minute, that has a more negative charge on the oxygen side, which is attracted to the positive side of other water molecules that have the hydrogen exposed to that oxygen. Because oxygen is more negatively charged and hydrogen is more positively charged. So what do we see here? We actually see the 2 oxygens coming together, and we are seeing the sharing of these electrons. And so that's oxygen gas. So what are the properties of water? Well, we know that water is liquid at room temperature. Liquid water does not change very quickly. It takes time. You got to turn the heat up for a while until the heat of vaporization occurs and you start to vaporize the water. Now, same thing with the water. It won't freeze very easily, so it takes a while, and the molecules of water cling to each other, cohesion, because of the polarity. So what does that mean, polarity? So what you see here is the H2O hydrogen bonds with the oxygen. What did I tell you? Oxygen is more negatively charged and hydrogen is more positively charged. So they get attracted to each other, so they cohesively stick together. This is how water is so fluid together all the time. Sharing is caring. They share, as you know. I showed you the covalent bonds of H2O, but then there's the polarity bond between one H2O and another H2O and another H2O, making a network. And that's why water is so fluid. All right, so now we move on to very relevant information, because if you're going to be nurses, you're going to want to know if someone hyperventilating is excessively releasing what? Carbon dioxide. All right, so think about all these things. We're going to have to know alkalosis and acidosis in the body. We're going to have to know respiratory acidosis, respiratory alkalosis, metabolic acidosis, metabolic acidosis. But before you do all that, you got to do the foundation. And here I am teaching you the foundation. Acids is basically any substance that when it breaks down releases lots of hydrogen. Some release some hydrogen, some release more than others. So for example, you probably didn't know this, but apple juice has a very low pH, meaning it releases a lot of hydrogen when it dissociates, as much as lemon. Milk is acidic. I don't know if you know this, okay? Bases are the opposite polar end, where a basic solution or a basic substance, when it breaks down, substances are taken up by hydrogen ions. And so when it gets released, it's going to release hydroxyl, OH negative. All right. So these are substances that take up hydrogen atoms or release hydroxyl ions. All right. So the pH scale is basically a measure of hydrogen ion concentration. And so the working scale is between 0 and 14, 7 being neutral. So water is around 7. Anything below 7 is going to be acidic. Anything above 7 is basic. Now, the concentration of ions between 1 and 7 versus 7 and 10 is completely whole different story. All right. So the higher up you go from 7 to 10, you're going to release more hydroxyl and less hydrogen, whereas 7 and below, you're going to release more hydrogen. Okay. So this is an example of a pH scale. I wanted you to see it so you can see that your stomach releases hydrochloric acid to break down the protein, which becomes multi-polypeptide chains of amino acids. So hydrochloric acid is very good at breaking up proteins and so that, and churning the food so we can break up the parts from, you know, chunks to liquid chyme, C-H-Y-M-E. This is the only exception in anatomy where we don't say chyme, it's called chyme, C-H-Y-M-E. You can learn about it when we do digestive system, AMP2, not there yet. Okay, so 0, pH of 0, that means like it's pure hydrogen. I mean, like massive release of hydrogen. Stomach acid is around 2, lemon juice is also around 2, vinegar, cola, beer is around 3, tomatoes around 4, black coffee is around 5, urine is around 6, 7 is pure water. You never want to drink seawater, it's high in salt. That's not good. Why is that not good? Well, water follows salt. So imagine you drink all the salt water, then all the water from your cells is going to leave and it's going to go into extracellular components. It can kill you. Bottom line, it could put your kidneys into failure. Don't drink seawater. Okay, so water has to be at 7, drinkable water. 8 is seawater. 9 is baking soda. The Great Salt Lake is 10. Ammonia, I know someone that actually tried to commit suicide with ammonia. It didn't work, but they pumped the stomach. But household ammonia, very dangerous. Household bleach, also very dangerous, very high basic hydroxyl release, okay? And then 14 is sodium hydroxide. All right, so that is my spiel on pH, very short and sweet, to the point. You can go study a little bit more if you want to get into it before we actually get into it. But when you get into AMP2 and we do respiratory system, we're going to talk about respiratory acidosis and respiratory alkalosis because it is of huge importance to understand, especially if you're going to be nurses. Hyperventilation, hypoventilation, hyper meaning excess carbon dioxide release from hyperventilation from anxiety attack versus hypoventilation, you're not breathing enough. All right, so dehydration versus hydroxyl or hydrolysis reaction. Let's talk about this. So shifting to another topic, we're talking about how we break down organic molecules. What's a dehydration reaction and what's a hydrolysis reaction? A dehydration reaction is actual removal of the water from the subunits that are linked to each other. So the removal of water from the units, okay, can actually create other units that are larger. Now, hydrolysis is adding water that breaks down larger molecules into smaller components. None of this makes sense until I show you how that happens. Here it is. Let me just diminish the size on this so you can see it better. Hold on. All right, maybe a little more. There we go. All right, so here we have two subunits that are put together because of a hydrogen and a hydroxyl end, right? So a dehydration is we're actually getting rid of water. So we're getting rid of this hydrogen and this hydroxyl, and we're making water. So it's dehydration, we're making water, but in making that water as a byproduct, the actual product itself is the two subunits coming together, okay? Now, what about hydrolysis? We got to look at it from this end. Here's two subunits together. If we add water in, hydrolysis, okay, hydrolysis is adding water. Okay, so adding water to these two subunits is actually going to break them up into this subunit with hydroxyl and this subunit with hydrogen, just like the opposite of what you see here. Okay. Now, moving on to another topic. Like I said, this is just a highlight of everything. The book goes into way more, and I believe the PowerPoint that was given to you based on the OpenStax anatomy book, which I have, is way more detailed. So I'm just giving you these cliff notes. So remember, what do you need to remember about organic molecules found in living organisms? This is it, okay? This is it. This is all you need to remember. But then we go into details. What are carbs? What are the details about carbs, lipids, proteins, nucleic acids? Okay. And we go over that in biochemistry or medical biochemistry, which is a very popular topic for nursing and med students. That is a requirement in some schools. So we touch upon it here with anatomy. So I think it's important that you understand what complex carbohydrates are, what lipids are, and the different types of lipids. Proteins are basically subunits of multiple amino acids put together, and we call those polypeptide chains of amino acids. And nucleic acids, which are basically the foundational structure of your DNA. All right, let's go over carbs first. So carbs are made of monosaccharides, which are basically, they like water. It's not like lipids that can't mix with water. If you ever put like olive oil in water, you know that it doesn't dissolve. It just kind of sticks by itself, right? So those are monosaccharides. Now, carbon, hydrogen, and oxygen is basically what you find in carbohydrates. And hydrogen and oxygen are in a 2-to-1 ratio. Okay, now the function is short and long-term energy storage. So let me give you an example. If you eat a chocolate bar, that's short-term storage. But if you eat like a baked potato, that's a complex carbohydrate, and that's going to be a little bit more long-term. But really long-term is going to be protein. So like if you're going to reach for a snack that's going to hold you over till dinner, then you could do a simple carb. But if you're not going to be eating and you don't have time to eat, but you can reach for a baked potato, even better, because that can last you 6 hours. So that's the difference. Okay, so a simple sugar or simple monosaccharide, okay, are rings. They all have carbon rings and a variety of different hydrogens, carbons, and oxygens. Hydrogens, carbons, and oxygens in different variations. That's all it is. Because what did I say? CHO, carbon, hydrogen, and oxygen, in which hydrogen and oxygen atoms are 2-to-1 ratio. Okay, so there's more hydrogen and oxygen than carbon in a 2-to-1 ratio in all carbohydrates. So we have monosaccharides, which are simple sugars, 1 ring, disaccharides, 2 rings, sharing with perhaps 1 atom, like this is an oxygen. And then we have complex carbohydrates like this, where we have polysaccharides, many branches. Polysaccharides are made of many carbon rings. Glycogen is the storage form in animals, including us. Starch is the carbohydrate storage form in plants. So what do we use? Yuck, I just accidentally spit on my laptop. I was talking too animated. Okay, so potatoes are complex carbohydrates, and you can see the complexity of the polysaccharides. Now let's go to lipids. What are lipids? All right, so what did we just learn? Just to circle back so you're not confused. We went over carbs, right? There's simple carbs, and then there was complex carbs. Simple carbs were monosaccharides, disaccharides. Complex carbs, for example, carbohydrates that are complex are potatoes. Okay, lipids, moving on to fats, lipids, molecules that do not dissolve in water, so they are hydrophobic. They do not like water. Your cell membrane is hydrophobic because the two lipids hang together. They stick together, kind of like getting two pieces of bread with mayonnaise, stick it together, and it's not going to open up. Okay, so lipids are super important in maintaining the cell membrane. That's why we have them in our body. Fats are actually good. It's just healthy fats, not bad fats. You know, there's the LDL and the HDL. We can get into that. But first, I want to just talk about lipids and what they are. They are energy molecules. So they're found in cell membranes. Fats and oils, phospholipids, steroids, and vitamins all are made of lipids. Okay. People don't think of vitamins as being lipids, but they are. So fats are usually of animal origin, and they're solid at room temperature. And this is why you can get atherosclerosis or plaque formation in the tunica media of the arteries, which you'll learn later in AP2. And so that plaque formation is due to the fats that form from animal fat, too much animal fat, and oils that are not good for you. And believe it or not, even some of the plant oils are not good for you. Okay, so olive oil is good for you, but you know, a lot of people using coconut, it's got a lot of saturated fat, just so you know. Anyway, so oils. So what is the structure of fats and oils? Here it is: a glycerol molecule and 3 fatty acid tails. So if I ask you, what is the structure of fats and oils? You say, oh, I know, it's easy. 1 glycerol, this is what it looks like, and 3 fatty acids make up a fat molecule. All right, so make sure that when you are buying food and you want to know exactly what's going on, you want to know the saturated fat versus the unsaturated fat. You want the unsaturated fat. The saturated fat is harder to digest. Think of saturated fat as animal fat, which is solid at room temperature, higher risk of atherosclerosis. Okay, what other fats are there? Guess what? Steroids. All kinds of steroids, all right? And we're not just talking about testosterone and estrogen. We're talking, for example, the cholesterol in your body, the LDL, the HDL, the high density lipoprotein, low density lipoprotein. All right. So the structure is always going to be 4 fused carbon rings. That's what a steroid looks like. And examples of that: 1, 2, 3, 4, 1, 2, 3, 4. But look, estrogen has a different variation on its tail here versus testosterone. And just that variation in a molecule makes us look different. How amazing. You know, makes us the male versus the female. And yes, men have estrogen and women have testosterone. It's just in a different balance, right? All right, moving on, we move on to proteins. Proteins are built, subunits are the amino acids, so they're built up out of amino acids. Polypeptide chains of amino acids make up a protein, which have to get folded one way, flat, folded, secondary, pleated, tertiary, folded 3-way, quaternary, folded 4-way, 3-dimensionally, that you can actually roll it up into a sphere. Kind of like a ball on a yarn on a ball, okay? And that's what makes up protein, because protein is very, very large, so it needs to be able to fit inside cells and places that it normally wouldn't fit if it wouldn't be pleated and folded up. Molecules get folded up, believe it or not. Okay, so what do amino acids look like? We have a lot of amino acids, but these are some of them: valine, glutamic acid, lysine, tryptophan. Tryptophan is high in turkey, as you know. Aspartic acid, cysteine, and tryptophan, apparently, everybody knows, makes you sleepy. But anyway, these are the amino acids. So, like I said just now, primary is a linear order of amino acids. Secondary is pleated so that it can fold up a little bit. Tertiary is 3D shape. Quaternary is like sphere-like so that it can really get packed in, okay? All proteins have primary, secondary, and tertiary structure, while only a few have quaternary structure because they're really large and they need to get to places. So here is primary, looks like a snake. Pleated, secondary. Tertiary is very popular. And then quaternary, think hemoglobin, because we have 4 million hemoglobin molecules in one red blood cell. And each Each and every single one hemoglobin molecule has 4 binding sites for oxygen. So 4 million hemoglobin molecules with 4 oxygen binding sites. That's 16 million ways that one simple red blood cell can transport. How about that? One red blood cell can transport 16 million oxygen molecules. Amazing, right? That in itself. Okay, so that was all about proteins. Moving on now, like I said, this is short and sweet. Nucleic acids. What would we do without nucleic acids? Well, there wouldn't be life on Earth because nucleic acids are the subunits of RNA and DNA, which makes up the function of every single cell. How about that? So super important. The function of cells that make up proteins. Protein synthesis occurs in the nucleus. We're going to go over that next week with cells. So the first part of protein synthesis is transcription, where the messenger RNA transcribes the DNA and reads it to make a protein eventually. And that mRNA is then going to go outside of the nucleus in the cytoplasm, attached to the rough endoplasmic reticulum, and then the factory making of amino acid polypeptide chains happens there. And we're going to go over it next week, and that's the translation process. And then packaging and delivery occurs by the Golgi apparatus and organelle inside the cell. Nonetheless, your DNA is super important, and it is found inside the nucleoplasm, inside the nucleus. Space inside the nucleus is called the nucleoplasm. So we're going to go over that next week. But for the purposes of this lesson today, make sure you understand that RNA and DNA is made up of these nucleotides. So what is a nucleotide? A nitrogen-containing base, a phosphate, and a sugar. I repeat, what's a nucleotide component made up of? A sugar, a nitrogen-containing base, and a phosphate. What are the 5 bases found in nucleotides? Okay, here we go. This is the foundational units of life on Earth. Adenine, guanine, cytosine, thymine. And guess what? In RNA, thymine is replaced with uracil. So RNA does not have thymine, it has uracil. So that's all you need to know. You have adenine is always going to pair up with thymine, and cytosine is always going to pair up with guanine. And now if a DNA is going to bind with an RNA that's transcribing, the RNA, if it sees an adenine from the DNA, then the RNA is going to bind with it as uracil, not thymine, because it doesn't have thymine. But if it's a DNA with a DNA hooking up together, forming the bond, as you can see here, T with A or A with T, G with C or C with G. So A with T, G with C, T with A, C with G. Okay, so they bind together. And then what else? You got hydrogen binding between the adenine and the thymine. Hydrogen binding between the guanine and the cytosine. Okay, and then if mRNA comes in to transcribe the DNA, you're going to take that uracil and replace it. Okay, because it cannot attach to adenine unless it's uracil. It does not produce thymine. So what's the difference between DNA and RNA? DNA, the sugar is deoxyribose. RNA, the sugar is ribose. The DNA has adenine, thymine, cytosine, guanine. RNA has adenine, uracil is replacing thymine, and it has cytosine and guanine. DNA will always be double-stranded. RNA is always single-stranded. So in summation, this is a summary of the macromolecules and everything that you need to know for chemistry to get by. Not much, okay? This is what you need to know to get by in anatomy, okay? To get by in microbiology, just minimal chemistry, chemistry for the body, biochemistry. So carbohydrates, all right, lipids, proteins, and nucleic acids. These are the 4 main macromolecules found in your body. Carbohydrates can be monosaccharides, disaccharides, polysaccharides. Here's the monomer glucose. Function, immediate energy, and some storage like glycogen in the liver. Lipids, fats, oils, phospholipids, and steroids. You have fatty acid and glycerol backbone. Long-term energy storage, as you know, bears can store a lot of fat. They do that. That's why they do that before hibernation. So they store up on lots of fat, right? Long-term energy storage. Great. What about proteins? Proteins are going to be super, super, super important for your body. Even your immunoglobulins, your antibodies that fight infection, are made up of proteins, okay? So proteins can be enzymes, proteins can be carriers, proteins can be hormones. Proteins have a huge role in the body. What are they made up of? Amino acids. What do they partake in function-wise? Metabolic reactions, transportation, regulation, motion, a lot. What about nucleic acids? Well, we know, we just went over it. DNA is deoxyribose, RNA, ribose. DNA has thymine, RNA does not have thymine, it has uracil. Everything else is the same. Adenine goes with thymine in DNA, guanine goes with cytosine, and reverse, okay? If RNA is going to hook up with the DNA, then if it's an adenine there, it's going to hook up as uracil with adenine, okay? Why do we care about nucleic acids? Because it stores genetic information to produce whatever is needed for the body. Everything from enzymes, everything from all kinds of different proteins to literally everything, the skin color, the eye color, and even the lactose that you need to be able to metabolize your milk. All right, that is it. That is your lesson for today. I will post this in the announcements and including with this PowerPoint, the video. All right, bye. Hope you enjoyed this lesson. Bye-bye.